Alright, so in the last video, we worked on, or the last couple of videos, we worked on reducing circuits, and we did a big, probably overwhelming circuit that we reduced down and ended up solving all the current and voltage drops for each of the, whole bunch of resistors that were on there. But I want to talk to you about what do you do if you can't reduce the circuit. So I'm going to go ahead and show you an example here. Oops, I got the wrong thing here. So let's say we've got a circuit that looks like this, a resistor, another resistor, put a resistor here, a resistor like this, and then a resistor in the middle, and then here and here it's just going off to a battery or something. We can probably add that on here if you want. We can say, alright, let's put a battery here. Okay, doesn't really matter what it is for this, but if you look at this circuit here, this is the thing we're most interested in. These can all be different R's or the same R if we want to make it a little simpler for our purposes. But all these resistors here, they're each all on their own in a way that we can't reduce them. None of them are in series or parallel with each other. So if I look at this one, if I, say I come along here, I send an electron through, it can go through this one, and it doesn't have to go through this one. It can go up this way and come around and skip that one, or it can come this way. So these two can't be in series because if I go this way, it can skip it. If I come the other way, I can skip each other. But there's a component in between them, so they almost look like these two almost look like they're parallel, but they're not, because there's this resistor right between them that's in their path that cuts them off. If this guy was missing, then it'd be easy. These two would be in series, these top two, these bottom two would be in series, and then the result would just be two equivalent resistors that were in parallel, and we could do it. But because of this resistor in the middle, there's no way I can reduce it. It cuts in between these top two and bottom two being series, and then it cuts in between, since we can't reduce them, to anything being in parallel. So there's nothing I can do to reduce this one. If you want to give it a try and see if you can figure it out, you can take a look at it, think it for a while. You'll see it can't be properly reduced. I mean, if you figure out a way to reduce it, then you're doing something wrong, basically, as far as these rules go. So we need a new set of rules here to try and actually solve a circuit like this. And so what we're going to have is Kirkoffs laws, or Kirkoffs rules sometimes. So there's two of them. The first rule is the current into a node is equal to the total current out of a node. This is a node, this is a node, this is a node. It's anywhere the circuit splits. Anywhere you're coming along a line, that's not a node. You get here, now it splits. So you could imagine if this was pipes, if this was piping, the water could get right here and it could split and go different ways. And if it was pipes, it would get here and the water could split and go different ways. So anywhere it can split and go different ways, that's a node. So the current in a node equals the current out of a node. Okay, that's just simple conservation of charge. Okay, that's just conservation of charge. Whatever current we have flowing, which is just moving charges, we have to have the same amount. We can't have current flowing into a node and then not coming back out. All right, it's got to go one way or the other. The second rule is, and if you think about this one, this will kind of make sense, especially if you think about the roller coaster idea. It's that the voltage drop around any closed loop is 0. Okay? It's 0. And it has to be. If you look at something like any closed loop at all, so like this one, here, this would, we thought of these cells as this is like a step up. This is the part of the roller coaster that, where it takes you up the hill. So it took us up the hill, we're floating around here, and now we come down here and we have to go down the hill, right? And then here we go downhill, and now we're along a wire. If we come back here, we have to be at the same height we started at. So if you think of voltage, kind of like how I've explained where it's like a topographical map, This takes you up the hill, down the hill, down the hill, and then you have to be back where you started because you're here. The wires can't take you up or down the hill. So you're back where you started. This isn't like one of those crazy paintings that are impossible. It has to be physically possible. You have to be, if you get back where you started, you have to be at the same elevation you started at. So that's a closed loop, has to be 0. This is a closed loop, has to be 0. This is a closed loop, it has to be 0. This one right here is a closed loop, it has to be 0. So wherever you go, if I go against the direction of the current, then I'm basically crawling up this hill, and then here I'm going down this hill, down this hill, down this hill, or back up this hill because I'm going against it here, and I'm back where I started. So you have to think about, if you go in the direction of current through a resistor, you're going down the hill. If you go the opposite direction of current, you're going up the hill, and it's an increase in voltage. If you go from negative to positive across a battery, that's uphill. Positive to negative on a battery, right? Remember, this is positive, this is negative, you're going downhill. So for cells, plus to minus is up, minus to plus is down. It's a decrease in voltage, increase in voltage. For a resistor, direction of current is downhill because they're reducing it, it's flowing down it. Opposite direction of current is uphill. So what I mean by here is this is a voltage increase, this is a voltage decrease, right here, voltage decrease, voltage increase. And if you just go through and check all these out and do it, you'll find that the voltage drop around any closed loop always gets you back to 0. So it could be like +5, -3, -2, and we're at 0. Okay? And that's pretty much it, these laws. And after that, it's just a matter of solving these. So let's go ahead and just try solving this one right now. And we'll try using these rules. So let's first say that we've got a voltage V here, and we'll say V equals, I don't care what we put, let's put 9 volts. And then why not, we'll just go with the 10 ohms for these again. So this R is 10 ohms, and we'll try working through it. So let's first start with our voltage drops, or actually let's start with our current. So the first thing I'm going to go ahead and just say is we're going to just guess. Okay, we're going to guess about different currents, because some of these situations you get to, you're just not sure, is the current going up or down, or which way is it going? And in fact, just to make this a little more interesting, I'm going to make this one, let's make this one here 2R. Okay, just to change it a little bit, so that'll be 20 ohms. I just think maybe we'll get a little bit more interesting of an answer. So I'm going to just guess about current. So I'm pretty sure this is the positive side, so I'm going to be pretty sure that this is a positive current here. I'm going to just call it I1. Okay? And so then I've got I1 right here going into this node, and it's got a split. And I think it's going to split so that I have something, I'll just call this one I2, and I'll call this one I3. And now I get I2 comes to this node, and it has to split. All right, it's splitting. So I'll have an I4, and then I'll have an I5 here. But now I'm wondering, is I5, is it going to go down? Because right here I've got I3 coming, and is it going to be trying to push current up, and this is going to be trying to push current down. And I'm not sure which way it'll go. So how do I know which way to point the current? And the answer is, it doesn't matter. Just pick a direction, just guess. I'm going to guess this way. I'm just going to guess it, and I'm going to call it I5. It's kind of hard to read, but I5. And if it turns out that I guessed wrong, when I end up solving for it, I5 will just be a negative value. It'll have a negative current, and I'll just know that I guessed wrong and that I have to just flip the direction around. So it really doesn't matter what direction you put these currents in. In fact, I could come right here to this one and just purposefully do it the wrong way, or I'm going to not do this one the wrong way. This one I'm pretty sure is going to be pointed this way. We had I5, so that's I6. And then we have this node here coming together. I have I4, I6. It has to be I1 again. So here's I1. And again, that's because that's the total current going through all of these has to be the total current coming out. So I know that this current and this current have to be the same. Whatever's coming out of the battery has to go back into the battery. Okay? Unless you have some short somewhere, in which case we're not dealing with that yet. Okay, so we've got this, and this should work. And usually if you have a short like that, that means your electronics aren't working because you've got something like touching a ground or something over here and all the currents getting leaked out. So let's see what equations we can write from this. This one tells me that I1 has to equal I2 plus I3. So I can write that down. I1 equals I2 plus I3. All right? Now let's look at the next one. I've got, how about this? I2 has to equal I4 plus I5. So I2 has to equal I4 plus I5. Okay? Because they're both, I2 is going into the node, I4 and I5 are coming out. I look at I3. I've got I3 going in, so I3, so we're doing this one right here now, right? We've got I3 going in. We have I5 going in, so I3 plus I5 has to equal I6 going out, right? Current in equals current out. And then the last one I have is I have to have I4 plus I6. They're going into that node. I4 plus I6. They have to equal I1 as well. All right, and now if I look at this, I have 6 variables, I1, I2, I3, I4, I5, I6, and I only have 4 equations. So that's not enough. So what we need to do is get some more equations, and thankfully we have another one of Kirkoffs' rules right here we can use to try and come up with some more relations. So let's take a look. Let's do a closed loop. Let's just go ahead and do this closed loop right here. So we're going to just start right here. I'm just going to pick a spot to start, and I'm going to go up. So that's plus 9 volts. So 9 volts. Then I'm going to come along here, and I'm going to go down. And I've got I3 times R. So if you look, remember that, maybe I'll just write it right here, V equals IR. So my voltage drop is just the current going through it times its resistance. So that's I3 times R. So it's minus I3 times R. Then I come along here, I'm going again in the direction of current. So it's just minus I6 times R. And that has to equal 0. So that was my one loop. And now I'm here, and I come right around, and I'm done it. So this was my loop. I went around this way and came to here. Okay, that was one loop. And so let's pick another loop. Let's pick this loop. We're going to start right here, and we're going to go around this loop this way. Okay, we can do that one. There are other loops we can do, but that's a pretty easy one. Let's do this. We're going to get, we're going up against the direction of current, right? So we're going opposite direction of current. That's up. That's an increase in voltage. So that's an I3R. Now here we're going in the direction of current. So that's a minus I2R. And because remember, IR is V. And then here we're going in the direction of current. So minus I5R. And that has to equal 0. And so now I have 6 equations with 6 unknowns. And I should be able to go through and plug in 9 volts for V, which I already have here, I guess. And I should be able to plug in the resistances and all this stuff and solve for each of these currents. I know what all the resistors are, right? So that's a known, known. And so I have 6 unknowns and I have 6 equations. And I should be able to go through and solve this. I don't want this to be a horribly long video, so I'm not sure I want to sit here and go through and solve it. But you have your choice of methods. You can start substituting if you want. You can say, oh, this is I1 equals I2 plus I3, so right here you can replace that and make it I2 plus I3, and everywhere you have an I1, you just replace with I2 plus I3. You can go through and you can do that, and that'll get rid of I1. And then you're down to, so this equation would be gone, and you'd be down to 5 equations and 5 unknowns. You could then take and solve for I2. I2 equals I4 plus I5, so everywhere there's an I2, you replace it with I4 plus I5, and that would be right there. And now that equation's gone, and you're down to 4 equations and 4 unknowns. And then you could solve this for I3, and it'd be I5 plus I6, and go and plug it in everywhere there's an I3, right there and there, and that'd reduce it down again, and you'd be down to 3 equations and 3 unknowns, where now all you have is 4, 5, and 6 is left. And then you solve one for I4 and plug it into the other two, and then solve one for I5 and plug it in the other, and you're down to just 1 equation with 1 unknown. And you can do that, or you can do the matrix method, and I'll set that one up for you just to show you. We want each of them in a form that they all kind of equal the same thing, and I'm going to put, whatever it is off to the side. So what we're going to want is we're going to want something like, and I'll do this in a different color. We're going to want some coefficient. We want each equation as some coefficient times I, something, like something A times I plus B times I2 plus C times I3 plus D times I4 plus E times I5 plus F times I6 equals some number. I don't know what it'll be. And so we want to get them all in this form, just in case you've never done this before. So this one is just I1 minus I2, not minus. Well, I can leave that there for now. I1 minus I2 minus I3 minus 0 I4 minus 0 I5 minus 0 I6, and then it has to equal to, that one equals to 0. Okay? And so that would be that one. This one would be 0 for I1, and then we'd have a I2, a plus I2, and a plus 0 I3, a minus I4, a minus I5, a minus 0 I6, and that one equals 0. And this one's going to be 0, 0 again, and then we'll have a plus I3, a 0 I4, a plus I5, and a minus I6, and that one also equals 0. So a lot of these are equaling 0, and I'm going to write them a little faster. I'm going to stop writing the pluses, and I'm going to move that minuses over, so that minus moves over a little bit. But I'm going to stop writing the addition signs. Really, I need to leave the minuses except for the minus zeros. I can remove those from there, because what I'm trying to do is we're going to make this look like a matrix. So let's do the next one down. 1, 2, 3. So this is 0. Oh, no, sorry. We've got an I1, a minus I1, a 0 I2, 0 I3, an I4, a 0 I5, and an I6, and that also equals 0. That was for this one. Now we come to this one right here, and we've got no I1s, no I2s. We have an R times I3. I'm adding these to the other side, so they'll become positive. So I have an plus R I3, no I4s, no I5s, and an R I6, and that has to equal 9. 9. I don't need to write the unit there, huh? I don't need to write the units on it here in doing this method. They're all volts, so they all ultimately have a unit of volt, so I don't need to write that. And then do the last one. Let's see here. We don't have an I1. We've got a minus I2 minus R times I2. We've got an RI3. We've got no I4. We have a minus RI5, and we have no I6, and that one also equals 0. And then what we're going to do is turn this into one big giant matrix. And if you don't know this method, you might want to look into it. And then what we can do is look and say, all right, we've got this matrix here. And what your goal is to start, if you don't know the rules here, you can take any single row or any multiple of any single row and add it to any other row. And what you're going to try to do is get it to be in a form, and I'm not going to write the whole thing out, where you have in one row you end up with something like you have a number, a number, a number, a number, and then a zero, a number, a number, a number, a zero, zero, a number, and a zero, zero, zero number, actually and numbers here on this side, whatever they happen to be. May or may not be zeros, but you want it to ultimately get to a form like this. So it takes a little bit of practice, but it can save you a lot of time from the substitutions because you're not having to write all the equals and plus signs and stuff like that. But you basically just start adding rows to other rows and multiples to other rows and subtracting rows from rows until you get to the point where you have only one variable in each row. Or I'm sorry, you get a row with only one variable in it, and then what you'll have, say this was I6, and it was like there was a 4 here and a 4I6 here and an 8 here. Well, then you would be able to know that 4 times I6 equaled 8. And you'd know that I6 was 2. Now I just made those numbers up because I'm not going to go through and do all this. It takes too long, and I don't want this video to be too long. But it's just another method to go through, and then you know what I6 is, so you can come back everywhere inside the matrix and substitute in 2 for I6 in this whole row, and then that basically eliminates that variable for you. So then you'd look at this next row and you'd say, okay, I know this number now, it's not an unknown, so the only thing I don't know is this, and you'd have something like 5I5 plus maybe 12 equals I don't know, 2. And so you'd look at this and say, oh look, I subtract the 12 over and I get that I5 is -2. And then you'd know what I5 was, and so you could plug I5 into these other rows, and then you'd only have the one unknown here, and you'd know I5 and I6, and you could write that equation out. And it basically is just a shortcut method for doing the substitution, but it might help you with doing these longer problems like this where you have a lot of substitutions to do. If you want to look into that method, that's really all I'm showing you, is look into this method. You really don't have to do it that way if you're uncomfortable with it, but get comfortable with it, and it'll save you a lot of time and effort. You can solve these problems real fast by setting up a matrix like this to solve a system of equations. All right, I think that's pretty much it for Kirkoffs rules then. Aside from my big showing you how to possibly solve this, you essentially just write it out, make sure you get as many equations as you do unknown variables, and then just go through and start solving it, okay, by whatever method allows you to solve it best. Okay, that's pretty much it for Kirkoffs laws.